Okay, I'm going to start. So welcome to our probability area we're meeting two. And I'm going to start our meeting by a review of what we have done 2 weeks ago in our meeting. In the introduction of the meeting 2 weeks ago, we talked about two types of probability. The first type is frequentist probability, and the second type is Bayesian probability. For frequentist probability, um, research people will use a trend from the experiment to determine the probability of an event. And for the Bayesian probability, which is also conditional probability, people use some of the evidences that we know in advance to determine the probability of one thing. There are two types of randomness. One type is called quantum randomness, and the other type is called classical randomness. So for the meeting last week, we taught the example we gave for the quantum randomness is the Schrödinger's cat. Quantum physicists refer to the state of not seeing what is going on in the box as the true state of randomness. The probability is 1/2 and 1/2. For 50% of the probability, the cat will live, and for another 50%, the cat in the box will pass. That is the quantum probability. And for the classical randomness, we're ignoring a lot of exterior conditions. The example we gave last week was the dice rolling. We're not considering how we roll the dice or what kind of surface the die fall on. So that is a classical randomness. And we said that in cryptanalysis, we're going to use Bayesian probability and classical randomness to calculate things. We also introduced cryptanalysis. Cryptanalysis is the study of using known language system, analyzing the language system in order to break ciphers. In the example we gave last week, we talked about the frequency. We analyzed the Caesar cipher in the perspective of frequency, and we compared the frequency for cipher of individual ciphertext letters and to the individual plaintext letters in order to eliminate some of the possibilities that we have and to break the code, essentially. Today, we're also going to use this method, but we're using it differently. I introduced you another category of cipher, which is polyalphabetic cipher. So for polyalphabetic cipher, we're using a keyword, or we're doing different alphabetic shifts for a cipher. So for the example that we gave, which is the Vigenère cipher, we have a keyword and we shift individual letters differently depending on the length of the keyword. We talked about how the Vigenère cipher works and the decoding mechanism with two known variables out of three. We use something called a Vigenère tableau. I could show you the tableau here. So this is the tableau that we use. So for this row here, we put the keyword, and for this row here, it will be the plain text, and we will put our ciphertext here, depending on the keyword. So in the example that we gave last week, we know the key and the ciphertext. We know two variables out of three. and the other one would be the plain text. So what if we only have the ciphertext? We do not know the key and we do not know the plain text. Now let me introduce you to Kasiski's examination. And from that examination, we could determine the plain text. We could decode the Vigenère cipher, only knowing the ciphertext for some cases. So the most important thing here is to figure out the length of the key. So this is the ciphertext that we're trying to break. And you can notice that in the ciphertext, there are 3 repetitive blocks of ciphertext. So the first one is marked in blue, the second one is marked in red, and the third set is marked in yellow. We're assuming that the repetitive blocks of words translate to the same plain text. Now notice that this might not happen, but we're assuming this will happen. So now we're looking at the distance from the first blue block here and to the start of the blue block. So this distance, the number of letters here will be a full rotation or several full rotation of the keywords. And the distance, the number of ciphertext letters from the start of the first block to the start of the second block is taken, and we will yield things from there. So I counted everything for you. So for the blue block, the distance between them would be 54 letters, and for the first red to the second red, 54, and from the second red to the third red, 24, and for the first yellow block to the second yellow block, that is 24. And we know that the distance here includes several rotation or a full rotation. So their common factor should be a factor of a multiple of our keyword length here. So let us find the common factors. So the greatest common divisor of 54 and 24 is 6. And every factor of 6 would be a potential key length. Here they are 1, 2, 3, and 6. We're assuming that this is not 1 because we're doing Vigenère cipher. It should be a keyword, not just one letter in the word. So we're considering the case of 2, 3, and 6. And then we could divide the ciphertext up into multiple parts. For example, if we are looking at the key length of 2, we might divide this up into 2 sets of ciphertext. So for the first set, we will have them congruent to 1 mod 26, and for the second one, maybe 0 congruent to 0 mod 26 because we have 26 letters. Then we could use a frequency analysis to determine them, like what we talked about last week. And if you notice that for the first part here, we're doing a frequency analysis for a block of words. We're not looking at individual letters, but we are looking at blocks of letters. So the frequency analysis is like this that we did last time. So we compare the most frequently used letter in a random literature work, and we make sure that they're written in the same language because we are looking at the same language system. And then choose a cipher, like different frequency of letters in the ciphertext. So the most frequent from the ciphertext and from the plaintext might correspond to a same shift. That is how we determine the actual plaintext by using frequency analysis to individual letters. And the plaintext here is this, and the key length here it's 3. So notice in the plaintext here we have a lot of repetitive blocks of words. Was a Catholic, and mother was a Catholic, father was a Catholic, and so on. I picked this excerpt on purpose because we have a lot of repetitive things. I know that from a transformation, from a Vigenère, like from the polyalphabetic transformation, we will get some repetitive blocks of ciphertext. Actually, we might not, but there's always a chance because we have so many blocks of different things. The method is going to be continued because we're going to talk more about it from the perspective of cryptanalysis and probability. We're still going to use some frequency analysis, but we're also going to combine the probabilities into it. And now on, Alan Turing will come onto the play. Before getting started on that, I'm going to introduce you some of the terms that we need to use in a probability theory. And so we're going to talk about 2 general terms. The first one is probability, and the second one is odds. So for the probability part, we're looking at the chance of getting something. We could use the number of times we could get something divided by the total number of cases. For example, look at the picture on the right-hand side. What is the probability for us to get 2 ones here, assuming these 2 are fair dice? So for us to get 1 on one of the dice is 1 out of 6, because we have only 1 case to get a 1, and we have in total 6 cases because we have 6 faces. And for this another one, because we assume that they are identical, and so the chance will be the same. It's also 1 out of 6, and the total probability should be 1 divided by 6 times 1 divided by 6, which is 1 divided by 36. And the odds here is the ratio between the probability and the 1 minus the probability. So the chance of getting 2 ones versus the chance of not getting 2 ones. So here we know that the probability is 1 out of 36, and the chance of not getting 2 ones would be 35 divided by 36. So the odds here would be 1 divided by 35. Now we're going to look at some math and some more terms. I'm going to change my screen so I could annotate on that. Just want to make sure that you could see this. Okay, you could. Okay, so this is a generalized version of Bayes' theorem. And we're going to first of all talk about Bayes' theorem visualizations, by some visualizations. And we're saying that the rectangle here is the sample space. And in our sample space, there are 2 independent events, event A and event B. They're represented as 2 circles. So the blue circle represents the event A, and the orange circle represent event B. And this intersection here is denoted by A intersects B. And so we need to know the possibility of event A to occur given that event B occurs. This is a probability for, we could consider this as the portion of the size of A intersection B in the circle B. So we're doing intersection of event A and event B divided by the size of the event B represented in this diagram. So it will be PA and B divided by PB. And similarly, we could determine the probability of B given A. The probability of that would be the possibility for two events to occur divided by event A. So we're doing the probability of that would be the portion of A intersects B inside the size of A. And from these two equations, equation 1 and equation 2, this part is the same. So we could merge them together into one equation, which is PA bar B, this bar means given, times PB equal to PBA times PA. And this will give us one example of Bayes' theorem. So the most common version of Bayes' theorem is written in this way. So for the diagram on the right here, we're looking at another case. And here we're assuming that we have two theorems. I'm here talking about theorems instead of, they're actually events, but I'm using theorems too, because we have whether a theorem is true or the theorem is false. That means that those two theorems are mutually exclusive. And we also need them to be collectively exhaustive. These are two things that T1 and T2 needs to satisfy. And mutually exclusive means that T1 and T2 does not have intersection. You could think of us dividing the event A into two subcases, and we want them not to have intersection because intersection will make things complicated. And they're collectively exhaustive because T1 and T2 combined together occupies the whole sample space. And we could also have more theorems. We could have a sample space with 3 theorems like this. So this will be T1, this will be T2, and this will be T3. And our blue circle here, it represents data. In realistic example, that this could be a piece of information that we know that will help us to determine the probability for an event to happen, or for our theorem 1 to occur, theorem 2 to occur. If we're talking about a true or false state, we might from the data determine the possibility for the theorem to be true or for the theorem to be false. And for the diagram on the right-hand side here, And for the possibility of D now could be written as this intersection time plus this intersection. So that is PT1 intersects D plus T2 intersects D. And this intersection could be written as D given T1 is true times PT1 plus PD T2 times PT2. So if we have more generalized case, for example, if we have a sample space divided up into n theorems, or divided up into n sections, and those n sections are collectively exhaustive and mutually exclusive, we will have the intersection here, the PD here, will be equal to the summation of PD given Ti is true times PTI. Now, if we want to know the possibility for T to be true given our data, that will be equal to PD given T, let's say PTI, and times PTI divided by the PD here. So the PD could be replaced by the summation thing, this whole thing here. This yields our generalized Bayes theorem. The more generalized version is given here by that. So for this part here, we're saying that this part is a posterior part, the posterior possibility. We want to know the possibility for the theorem to be true given data. So sorry, this is wrong here. Should be T1. And this is a likelihood. This part here is a likelihood. And this is the prior probability for us to know that part of our theorem is true. For example, when we were talking about something is true or false, we have two T's. We have T1 and T2. And T1 would be for an event to be true, and T2 would be event to be false. And the thing on the bottom here is called a marginalization. And T represents theorem and D represents data. Now let us ask a question. What if we want to know the posterior odds? What can we do now? So for the posterior odds, meaning that we want to know what is PT given DI, PTI given D divided by P negation of T given D. So which yields the theorem here. We are just replacing things by this formula here. And this also works for the negation of Ti, because if we have only two things, we're doing, this is T1 and this will become T2, but not the negation. If we only have two T's occupying the whole sample space, like how our illustration shows. And this will give us this. So if you notice, this is the posterior odd, the prior odds. This is what we said, the posterior odds. And this formula could be generalized and extended. The thing we want to know is that we want to, sorry, this is wrong here. We should use the previous thing. Just ignore this whole thing. The first thing that we should time this whole thing to is the prior odds. The odds for the theorem to be true divided by the negation of the theorem. And then we have different datas. This means PD1 T. This is PD1 negation of T. If we have different pieces of data that we know, you might ask why we're talking about theorem and data. We might have one assumption that we want to know about, but we also know some pieces of evidences in advance. And this posterior odds here will help us to analyze the odds for the assumption to be true versus the assumption to be false. So we have the prior odds, which is the possibility for a theorem to be true divided by theorem to be false. And we have a set of data, some evidences that we know in advance. So accordingly to the factor principle, which is also the posterior odds that we yield from the Bayes theorem, we time that by the data is true when given the theorem is true divided by data is true given theorem is false, and we time the likelihood of the evidences to get the posterior odds. And now let us look at one example with fake stats. The stats are what I made up. So this is a case of the first visualization that we see. We have event A and event B. So for event A, let us assume that is a possibility for people to include name in their passcode. And for the another circle, let us say that it is a possibility for people to use birthdays in their passcode. We want to know we have 1/4 of people using birthdays in their passcode. Among them, 1/3 also incorporate their names. We also know that 2/3 of people use names in passcode. What is the probability for a person to include their birthday in their passcode, given that passcode involves their name? So we want to find out the possibility of B given N. So the possibility of for people to have name in their passcode, given that they also incorporate birthday in their passcode, is 1/3. And for people to incorporate their birthdays in their passcode, it's 1/4. And that is divided by 2/3, which gives us 1/8. And next, we're going to look at something related to Vigenère cipher. So we're given a Vigenère cipher was given length of the keyword. We represent them in this way in a matrix. So the horizontal distance here, the horizontal number of letters here represents the length of the keyword. And the vertical length here represents that we have 6 blocks of ciphertext. So if arranged in a
common
way, this would be PWGFAR UIRHXY and so on. We're also given that a frequency counter. So this is taken from a normal English text. And we also assume that this ciphertext here is written in English. So we want to know the odds for the key of the first column to be B, which means that the whole alphabet is shifted afterwards one. So P in the plain text would be O. This is a factor principle that we have. We got this from the Bayes theorem, and the prior odds of B is 1 out of 25 because we have B is one letter out of 26 letters in total, so that is 1 divided by 25. And for us to getting P, if B is the key, means that the cipher letter P translates back to O. So the possibility for that, according to our frequency analysis, should be 29 divided by 462. And then getting P if B is not the key means that we have 25 equal possibilities, which means that we need to divide 1 minus 462 by 25. And we time things so on and so forth, going down from this column. Why we're going down from the column? Because the column is encoded by one same letter in the keyword. We're arranging things in that way, and this is the length of the keyword. So we know that each column uses the same key letter. And our odds for the key is actually graded. It could be graded by a unit called deciband, which is from the term decibnage. So one individual thing here is graded by deciband. Deciband is a unit of evidence referred to by Alan Turing. And the logarithm of this factor taken to the base 10 to the 1/10 is called the decibnage in favor of the theorem. In other words, we're saying that a piece of evidence is worth a deciband if it increases the odds of the theorem in ratio of 10 to the 1/10 divided by 1. And so using logarithm, that will be 10, we're taking 10 times the log of this. So log is base 10. So we do this to all the letters in the column here, and the same method goes on. And we yield a grading for all the letters by using different keys. We also need to change the key here. And this process is a bit complicated. This could be done by a computer. So the grading that we have actually tells us a possibility for things to happen. Let us get back to examine the weaknesses of Kasiski's examination. So the first weakness of the Kasiski's examination is that we're not guaranteed to yield same blocks of ciphertext that translates back into same blocks of plain text. For example, in the previous ciphertext, we have two first blocks of was he Catholic, translating back to the same thing, and the blocks afterwards translates to different things actually. And secondly, we're not guaranteed to have a block of same ciphertext. So there are possibilities for us to not getting blocks of ciphertext, and that is quite common. So the Kasiski examination cannot be used to all the Vigenère cipher. So we could, if you're interested in that, you could explore a bit more information about how to decode Vigenère cipher when we only know the ciphertext. The frequency analysis might be a way. And the Alan Turing's examination for the possibility will also be something that you might want to look at. So for the references, I used an introduction to mathematical theorem, cryptography. So the authors are Hofstein, Pfeiffer, and Silverman. And I also used the application of probability to cryptography by Alan Turing. So the whole concept of the principle, like the factor principle, and also how he incorporates the classical randomness based in probability into cryptanalysis is worth mentioning here in our meeting. So that is the end of the meeting. Thank you.